Segment 22, Part A, the solar atmosphere and line formation. In this segment, we'll discuss how lines form in the solar atmosphere, the spectral lines that characterize the Sun and other stars, and we'll talk about the atmospheric structure of the Sun. If you take a picture of the Sun is made completely of gas, and you're seeing into the depth where that gas becomes opaque. You're seeing just as far as you can see and no farther. And there's not a solid surface that you're seeing to. If the Sun is opaque, then why does it show absorption lines? So if you take a prism and you split up the light of the Sun, you see the colors of the rainbow. But if you split it up even more finely, as Fraunhofer did for the first time about 2 centuries ago, you see that these colors are punctuated by dark lines, places where there's less emission coming through to us at those particular wavelengths. So how does this happen? In order to understand that, we have to look at the structure of the Sun's atmosphere and apply something of our knowledge of black bodies. So the temperature of the gas in the Sun, starting from the middle where it's a few million degrees, drops steadily until you get near the outside. At a point in the photosphere, just above the photosphere, you reach a temperature minimum, and then the Sun's temperature reverses and goes to higher temperatures going up. But this gas is largely transparent, and so is not relevant in most cases. We'll see where it becomes relevant in a little bit. So how do we go about forming these absorption lines that we see? This I don't have a good illustration for, but let me walk you through the process. The Sun's temperature drops towards the outside to the photosphere steadily, and then from the photosphere up continues to drop a little bit and then starts to rise again. When you look at the Sun, you see into the point where it becomes opaque. Think about if you're driving in the fog, what you see in front of you is this white wall of fog, and as you move along, that white wall moves with you until there's some kind of a solid object, and all of a sudden you see that solid object as well. If you're diving in murky waters, like in Lake Travis, the same thing will happen. You'll swim along, and then all of a sudden you'll see the barracuda, although of course we don't have those in fresh water. And if you're going towards a distant set of mountains, you'll see just murk in the distance until finally the mountains will appear out of that murk. What you're seeing before you see the shark or the mountains or the lamppost is the place at which the atmosphere becomes opaque. Now think about it now instead of in distance but in terms of wavelength. The Sun's continuous opacity is the opacity of the ability of the Sun to absorb light at all wavelengths, varies very slowly with wavelengths. So in between the lines we see into about the same depth. This is what actually defines the photosphere. This is the place where the atmosphere becomes opaque. But at particular wavelengths where different atoms can absorb light by jumping from a lower state to a higher state, the opacity is higher. So as we look into the Sun, the place where a photon can get out to get to us from that place at that particular wavelength has to be closer to the surface so that there's fewer atoms in front of it because the opacity is higher at that particular wavelength. These atomic transitions add opacity. We don't see in as far, and therefore we see to a place above the photosphere where the temperature is lower. Remember that lower temperature black bodies have lower fluxes at all wavelengths, including this particular wavelength. So there's less flux at that wavelength. And as a result, we actually see a dip in the spectrum where the intensity is lower. The quiescent surface of the Sun, the photosphere, is highly reticulated. Reticulated means this kind of granular picture, like a reticulated python has all of those little markings on it. Why does it look like this? Why does it have these bright areas punctuated by dark lined areas? This is a result of a combination of temperature effects and motion in the Sun's atmosphere. The Sun's atmosphere is made up of a set of granules. They're about 700 kilometers across, so about the distance from San Antonio to Dallas. And in these granules, hot material is welling up. It's coming up from inside the Sun. And when it gets to the photosphere where the atmosphere can transmit light, it radiates away energy that cools it off. And then the cooler material flows down at the edges of these spots. So this is a part of the process of convection, as you might see if you heat up water in a pan to close to the boiling temperature. The sinking gas is cooler, and therefore, because cooler black bodies emit less than warm black bodies, it looks darker. And the warmer gas in the middle is hotter, and so it radiates more. And so you see these bright spots with dark edges on them. The outer part of the sun, we mentioned before, which is known as the solar corona, is very extended but very, very tenuous. This gas is not part of the normal equilibrium heating of the sun. It's heated by acoustic waves, shock waves from sound that go into this thinner gas and heat it up to very high temperatures, to about 1,000,000 degrees. Since it's transparent at visible wavelengths, the normal black body laws are not relevant here, and we see right through it to the sun's surface. But when this is a picture taken during a solar eclipse where the main photosphere of the sun is blocked, and all you're seeing is the very, very much fainter optical emission from this outer region. When you take a picture in X-rays, however, now you don't even need to block the surface of the sun, because this 1,000,000-degree gas is much, much brighter than the solar surface. The dark you see there is the solar photosphere, which is only about 5,800 degrees. It doesn't emit very many X-rays at all. But the disk as a whole, above the disk as a whole, is this hotter 1,000,000-degree gas which emits copious amount of X-rays, and that's what we're seeing in this picture here. Those dark areas where you can see through to the photosphere are known as coronal holes. It's just areas where there isn't as much hot gas, and that exists because of the configuration of the magnetic field, which is something we'll be talking about in the second part of this segment.